So for this video, we're going to look at homogeneous linear differential equations with constant coefficients. And so this is part 2. Okay. So before we had said that we had several cases. One case when we have two distinct roots, then we have repeated roots or complex roots. So let's look at an example. And so we want to find the general solution to this differential equation, y double prime plus 5y prime plus 6y equals 0. And again, we can see that this is a second order linear differential equation with constant coefficients, and it's homogeneous because it's set equal to 0. So here's our solution. So for this type of differential equation, we're going to assume that our y is of the form e to the rt. It follows that, we are going to have y prime. If y is equal to e to the rt, y prime is going to be r e to the rt, and y double prime is going to be r squared e to the rt. So plugging those in, we get r squared e to the rt plus 5r e to the rt plus 6e to the rt is equal to 0. By factoring out that e to the rt, we get r squared plus 5r plus 6e to the rt is equal to 0. And so I know that the function e to the rt does not equal 0 for any value of t. Therefore, the solution must exist when in this polynomial. So if I factor that out, I get r plus 2, r plus 3. So our solutions are r equal -2 and r equal -3. So that means that we have solutions of the form e to the -2t and e to the -3t are solutions. And in fact, we'll find out that these two solutions are linearly independent. And so really any solution will be of the form of some linear combination of these two. So all solutions will be of this form. Y is equal to some linear combination of these two. So it could be some constant times this plus some other constant times this. And this linear combination of this solution is going to, all the solutions of this differential equation will be of this type. Okay, so we're going to be talking again about solutions of linear homogeneous differential equations with constant coefficients. And on the last slide, I was claiming that the solution had to be some linear combination of the two solutions that I found. So now we will deal with why these solutions must look the way they do. And why the solution we find is unique.
Try a time.
Is unique. So basically it has to do with some concepts from linear algebra that you may have seen before if you had linear algebra. And those concepts are linear independence, and spanning. Okay. And so the basic idea from linear algebra is that if we have, well, in linear algebra we're talking about vectors, of course, or sometimes we talk about functions, but if in linear algebra, if we have two vectors that are linearly independent and that span the space, then we can say that that can be a basis for that space. Or in other words, I can get anywhere in that vector space by traveling along some linear combination of those basis vectors. And so we're going to use a similar idea here. So we can know why the solutions are unique if we can find a linear independent set that is as the same dimension as the solution space. So something that we need to do is, in linear algebra, we have ways of showing that vectors are linearly independent, but how do we show that a set of functions is linearly independent? So the answer is something called the Wronskian. So we can compute the Wronskian, and I'll just show you a simplified case of it where you have two functions. So let's say the Wronskian of two functions, y1 of t and y2 of t, is given by this, and here's the notation: the Wronskian of y1 and y2. And the Wronskian is actually another function of t. And so that's going to be determined by this determinant. And so we'll have y1 of t and y2 of t here. And then we'll have y1 prime of t and y2 prime of t. And then we will say that that's equal to, so this is just the determinant from linear algebra, or you may have used determinants in calculus 3. So it's going to be y1 of t, y2 prime of t, minus y2 of t times y1 prime of t. Okay, and so how does this tell you whether or not it's linearly independent? So the functions y1 of t and y2 of t are linearly independent
Hey, can I get a little slip thing? Oh.
if there is some value of t for which w, y1, y2 of t is non-zero. Okay, and if we know that, then we know those two functions are linearly independent. So if we look back at the previous example, we found that the solutions to y double prime plus 5y prime plus 6y were, we found y1 was e to the negative 2t, and y2 we found was e to the negative 3t. And so The question is, are these two solutions linearly independent? So I can compute the Wronskian of y1 and y2. And the Wronskian, again, is going to give me a function of t. So I want to compute the determinant of this matrix. So I'll put y1 here, e to the minus 2t, and then the derivative of y1 is negative 2e to the minus 2t. And then I'll put y2 here, e to the minus 3t. And the derivative of y2 is negative 3e to the minus 3t. And if I compute this determinant, I'll have negative 3e to the minus 2t, e to the minus 3t, minus negative 2e to the minus 2t, e to the minus 3t. And so I get out of that negative 3e to the minus 5t plus 2e to the minus 5t, which gives me negative e to the minus 5t. And there is a t, in fact, any t that I plug in here will give me a non-zero value for this function. So any value of t will give me that negative e to the negative 5t is non-zero. So, and because I know the graph of this thing is going to look like this kind of a thing. So it actually has an asymptote there at 0, so it's never going to be 0. So thus, this y1 and y2 are linearly dependent. Okay, I also know that since this is an order 2, second order differential equation, that the dimension size of my solution space is that my solution space is going to be 2-dimensional. And so since I have two linearly, oh sorry, that's supposed to be independent. Oops. Independent. Okay, so since I have two linearly independent functions, I know that those form a basis of my solution space. So all solutions to y double prime plus 5y prime plus 6y equals 0 are some linear combination of those two functions. So we're going to have like some constant e to the minus 2t plus some constant e to the minus 3t.